So for section 1.6, which is calculating limits using the limit laws, I'm going to start off by showing you a few graphs to talk about the limit laws, and then I'll come back to the guided notes. So I want you to take a look at the top of your page, which says there's a first line. I'll fill that in a minute, but we have properties. So let's say we have a function f of x, and we have a function g of x, and they have these limits L and M. C is just a constant. So we have these limit laws that tell us if you have this thing, the limit's going to be this thing. So I have on our graph here the 7 different properties and examples of those. So we'll take a look at them. So the first property is the limit as x goes to a of c is c. And what that's telling us is that if you ever have a function that is a constant, that the limit as you approach any x value is that constant. And you can see from the graph here that as you approach -2, you have the value of 4. As you approach 1, you have the value of 4. So any x value that you can imagine, that limit is always going to be that constant, in this case, the constant of 4. So that's why we have limit law number 1. Limit law number 2 is the function x. So the limit as x approaches a of just x is a. And the reason for that is because when you think of x, that is a line that has slope 1, so that every x and y value is the same. So it's basically saying as you approach any x value, your y value is going to be that same x value. And again, that's because of the type of function that it is. So we have 2, 2, 3, 3, and of course any value in between as well. So if you ever have just, f of x equaling x, that's going to be what you do if you're looking for the limit to any x value. Now getting into a little more exciting here for number 3. Number 3 tells us basically that if you take a constant and multiply it by a function, that's the same as taking the limit of the function and then multiplying it by the constant that's in front. So I'm going to show you, let's show you first just x squared. So everybody's really familiar with x squared. Here it is. So let's look as x approaches 1. So as x approaches 1, we see that the limit is 1. If I multiply this by 2, what we're going to see is as we approach 1, we now have the limit 2. And that's because that's the same as saying, well, the limit for x squared as x approaches 1 is 1, and we multiply that by 2 and we get 2. So you can always pull out that constant from the limit if you want, find the limit and multiply by the constant. So what I want us to really see now for the rest of the problems is that for x, the limit as x approaches 1 is 1. And for my function h of x, the limit as x approaches 1 is 2. So I just want you to notice this value and this value. So what property number 4 says is that if you add or subtract two functions together, you can add or subtract their limits at a value. So as an example, here it is. So hopefully this isn't too hard to see, but the black is the combination of the two, is the addition of g of x and h of x. And what you see is that one of them has the limit of 1, one has the limit of 2, and if you add those two together, you have the limit of 3. And so, as you can see graphically, that's an example of that limit law. You can also multiply two functions together and therefore multiply their limits. This is property number 5. So this one's probably even, I can kind of come in here a little bit, but what we're seeing here is this combination of the two functions is in red. And so we have our limit of 1, we have our limit in the purple of 2, but 1 times 2 is just 2. So that's why you have that same limit there happening with the multiplication. For the division, which is property number 6, you can divide the two limits. So here I have g of x, which is x, divided by h of x, which is 2x squared, and that's the blue, so it gets a little bit crazy there. But what you're seeing is f of x has a limit of 1, g of x has a limit of 2 as x approaches 1, and if you take 1 and divide it by 2, you get 1/2. So that's what's happening right here. But that is what you can do. So the point is you could find each one of them separately and then just divide them instead of having to do more work than that. And then the last example is simply our h of x, which is the 2x squared right here. if we were to cube it. So what I want you to see is that we have at 1, we have that limit of 2. But if we cube it, it's the same as just doing 2 cubed. And so the limit is now 8, which is 2 times 2 times 2, or 2 cubed. And that was property number 7. So those are examples of all the properties, and now we're going to use them in a capacity where we're writing some stuff down. The guided notes for section 1.6, calculating limits using the limit laws. So far we've looked at limits graphically. How else? You might remember we were doing numerically. And now we are going to be able to do algebraically. And that's because now we're going to do a lot more with some algebra skills that we have. So these properties I talked about in the beginning of the video. I showed some examples of that, but we'll use them for this. So I do think at this point it would be a really good idea. We have 3 functions. We just have this value a. We don't know what a is. It doesn't matter. We're just given 3 functions. We're told what the limits are for those 3 functions as x approaches this a. And what I want you to do is just take a moment, please pause this and take a moment and see if you can come up with the answers using the limit laws from above, and then unpause it and see if you got them right. Okay, go. All right, now we're back. So looking at the first one, it says find the limit as x approaches a of f of x of g of x. So what we've learned is that because those 2 limits exist, the limit of combining the 2 functions together and adding the 2 functions together is just adding the 2 limits together. Similarly, we have f of x times g of x, and again, because those 2 limits exist, we can multiply their limits together, and that's the answer for that. For the next one, you really just want to remember that f of x, the square root, is the same as f of x to the 1/2. So what this tells us from limit law number 7 is that this is the same as taking the limit for f of x, which is just 2, and raising that to the 1/2. So 2 to the 1/2, square root of 2, however you want to say it. For number 4, we saw this. We can take the 2 functions and just divide them. So we have h of x, which is 0, divided by f of x, which is 2. These are both real numbers. When we take 0 and we divide it by 2, that is just 0. So 0 divided by anything, anything that is non-zero is 0. So that's okay. That just means that the limit is 0. However, for the next one, you may probably not be surprised that if we were to flip these 2 functions and then have 2 divided by 0, that is not something that we can have. And so in this case, we would not be able to use the properties to come up with an answer. So it's not necessarily saying that it doesn't exist. We don't know what it is, but the point is we can't use the limit laws to come up with it because we don't have, we can't divide by 0, and we have to have that in order to use that limit law in that way. Okay, so I will not expect this of students all the time, but I do want you to notice that once you have something like this, notice this is like 3 terms here. We can use the limit laws on this. Again, it's just to kind of show you to the point where we can kind of make our lives easier, but we can split these up. This is because of the addition, subtraction, and kind of all these things that we have. But we have, I can put that minus on the outside because that's a constant. I can actually put the 3 on the outside because of what we learned already from the limit laws. I have x there, plus, and then we have the limit as x goes to 2 of 1. So thinking about what we learned, we know that the limit as x goes to 2 of x is just 2, and then if we square it, we get 4, and minus 3 times the limit as x approaches 2 of x, we've learned, is 2, and the limit as x approaches 2 of 1 is just 1. So we end up with 4 minus 6 plus 1, or negative 1. But what I really want you to see here, the key thing to see, is that This is the same as if we just plugged it in. And that's where we're at right now. So our next theorem here says if you have a polynomial, then the limit as x approaches a of that polynomial is just p of a, meaning it's just plugging a in to the polynomial. And that's because polynomials are smooth and continuous. And so their domains are all real numbers. You should be able to plug in a value and out will come a real number. It's very, very similar. The corollary that we have after that is very, very similar. It's talking about rational functions. So you have those fractions, but each of those pieces is a polynomial. So in general, you're probably pretty good, except that we don't want that denominator to be 0. If that denominator is 0, this corollary is not true. Otherwise, you can also just plug in and see what you get. So let's take a look. If we start out with a limit as x goes to 1 of what we have here, the first step in taking a limit, plug it in. Plug it in and see what you get. Because if you plug it in and you get a real number, you're done. You're done. So if we plug in 1, we get 1 squared minus 3 times 1 plus 1. In the denominator, as you can see, 1 squared plus 1 plus 2. So that's going to give us a negative 2 plus 1. It's going to give us a negative 1. In the denominator, it's going to give us 4. So we get negative 1/4. So that is our limit. We plugged it in. We got a whole number. We don't have to graph it. We don't have to find values that are really, really close to 1 on either side. We plugged it in and we got an answer, so we're good. For the limit as x goes to 0, again, first thing you do is plug it in, see if you get a real number. So we get 0 plus 2 times 0. I mean, if you want, I can say 0 cubed. Plus 2 times 0 plus 4. And looks like we get the square root of 4, and that is 2. So again, we're done. We're done. But I have a feeling that you realize that something else is coming. So taking a look at the next example as x approaches 3. I'm going to do this over here because I know what the answer is. So if we were to plug it in, notice in the numerator we get 9 plus 6 minus 15. In the denominator, we get 3 minus 3. So what we get is 0 divided by 0. And that's not a thing. It's not a thing. So in a case like this, if you ever get 0 over 0, you need to think, I need to do some algebra. And what algebra you do is different depending on the situation that you have, but there's typically some sort of manipulation you can do to what you have to help you with your answer. So what do you notice about the numerator, x squared plus 2x minus 15? Anybody? So hopefully you see that it is something that can be factored. It's a trinomial that can be factored. So take a second and factor that. 2 numbers multiplied together give you negative 15. Added give you positive 2. So here we are. And this is not a surprise. Hopefully what you see is this is just a line with a hole in it. And that hole is at 3. So what we do by factoring it is we recognize that we have these 2 common terms here, these 2 common factors, I should say, common factors that can be simplified. So what we started with is the same as the limit as x approaches 3 of x plus 5. And what we notice is you can plug x into this, x being 3, and get 8. And so now you're fine. So this is just a situation where you have this line, and then there's just a hole at the value 3, 8. But there is a limit because we get infinitely close to it. There's just a hole there. But algebra is what got us there. Now, the next one, I'm going to do the same thing over here. This is your next page. But the limit as x approaches 1. Notice in our numerator, I got to start out with plugging it in. I plug it in, and I'm going to get the square root of 4 minus 2 over 1 minus 1. No surprise here, we get 0 over 0. Boo. But that tells us algebra. Now this one's not quite as easy as factoring, but I will say factoring is really common when you have those polynomials. But in a case of a root, a square root specifically, there's something that we can do to help us. And you may or may not know. And if you don't, that's okay. but we're going to multiply by the conjugate. So you want to remember that the conjugate is the same as what we have in the numerator, except, as you might be able to notice, it has the opposite sign in between. The reason that we do this is because we are trying to see if we can take away that square root and, see if something happens, and something will happen. Notice that the two binomials that I'm multiplying in my numerators are the difference of squares. What that means is, and you can do this, out if you want on the side somewhere, but what you should see is you're taking the square root of x plus 3 and multiplying it by the square root of x plus 3. And because those two things are the same, you're squaring something that is a square root, and that's going to give you x plus 3. And then you're going to take x plus 3 and multiply it by positive 2, but then you're going to take x plus 3 and multiply it by negative 2. So those two terms are going to simplify to 0. And then when you multiply the two last things together, you get a minus 4. Now, if you're expecting great things out of the denominator, it's not going to happen. Your denominator is still just x minus 1 times the square root of x plus 3 plus 2. But you should see, and actually I have made a very common mistake that I did not mean to make, but I can't forget my limit. The limit as x approaches 1. That's got to be right here, and I left it out, and I shouldn't have. Always got to have your limit. So limit as x approaches 1. But look at now, look what happens to my denominators, or my numerator, excuse me. So notice my numerator is now x minus 1. Woo! X plus 3 minus 4. And so what that means, not surprisingly, is that that's going to simplify now with that factor in the denominator, and that is made to happen. So I'm going to have this here, and then I'm going to be able to simplify my numerator. Don't forget that that's just multiplied by 1, and then I'm going to come down here and have the limit as x approaches 1. My numerator is now 1. My denominator just has the square root of x plus 3 plus 2. So notice we got rid of the thing that was the problem, and that was that x minus 1 in the denominator. It's now gone. So now when we plug in 1, you should see that we're going to get 1 in our numerator, because nothing happening there, it's just 1. In our denominator, we have the square root of 1 plus 3, which is 4. So square root of 4. Square root of 4 is 2, and a net plus another 2 is 1/4. And so now we get our answer of 1/4. But algebra was required to make that happen. Now let's take a look at some piecewise limits, and we've already seen these, so it's just kind of a reminder that when you have a piecewise function, notice it is not actually, we don't have continuity, it's not continuous. We have that little jump there. We'll be talking more about this in 1.8, but we have this little jump at 1. So notice that. But we can look at each side. So coming in from the right-hand side is saying what's happening as we come in this way, and you can see we come down, and our y value, which is what a limit is simply 0. And then think about what we have coming from the other side. Yes, coming in from the other side, we have 1. So that's what's happening as we approach this way. We're up, 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 up. Obviously, the limit for x approaching 1 for this function does not exist, because the two functions there, the two limits coming from each side are not the same. Now the last bit of section 1.6 is a theorem and then a squeeze theorem. So the squeeze theorem is kind of cool, kind of exciting. Also, kind of interesting if you take a look at the picture down in the corner there. Oh, that tells me I'm going to have to move my face because that's usually where my face goes. All right, so we have a theorem up at the top. It basically just says if you have two functions and for one of them, the y value is always less than the y value for the other, and you have limits that exist, then the limit of the one that is the smaller y values is going to be less than or equal to the limit that has the larger y values. So it's telling us something about if you have y values, so if you have a function that's always up here and you have another function that's always down here, then the limit, as you're approaching up here is always going to be greater than the limit as you're approaching down here. And that makes sense because if the y values are higher, then the limit should also, if one of them has a higher y value than another, then it would make sense that the limit would be a higher y value than the other. but there's a place where it helps us, and that's called the squeeze theorem. And the squeeze theorem is so named because it's really the idea of, let's say you have a function that you can squeeze between one function and another function. So it's always greater than or equal to one function, less than or equal to another function. So it's in between the two functions. You got a function here, it's in between the two functions. Okay, and again, we have to remember that it doesn't matter if there is an actual value at the limit you're approaching, but we've got that. So you have these limits at the smaller function and the larger function. And the kind of interesting thing is, if you find that you have two functions where both their limits are something, and you have this other function that's in between those two, well, then it has to have the same limit as they do. Here's what I mean by that. So we're going to take a look at this limit. And its limit as x approaches 0 of sine of pi over x times the square root of x cubed plus x squared. I get it. This function, crazy. But we don't have to worry so much about that fact. So we're just going to squeeze it, okay? So we're going to squeeze it. We're trying to we already know that it's 0. We're just trying to show that. So the way that we do that is, first we note something about sine. So we note that sine of x has a range, okay? Sine of x has a range. We know that the y values for sine is always greater than or equal to -1 and less than or equal to 1. And what we should also remember is that does not change even if you put something inside. So you can change anything you want on the inside of a sine, and it'll stretch it or it'll compress it, but it's never going to change its height in this way. So it always still has that range. So that tells us that we can first write sine of pi over x is less than or equal to 1, greater than or equal to -1. So notice that I'm starting to try to come up with a couple functions that then I can end up making the squeeze with. So we have this. Then what I'm going to do is I'm going to note that the square root of x cubed plus x squared is always positive. So if I multiply it through by that piece, now I'm not affecting the limit. I'm actually starting from the beginning here by writing that first line. But if I then multiply through, I have the sine of pi over x times the square root of x cubed plus x squared less than or equal to. So I'm just, those three pieces are all getting the multiplication by this other piece that we have. So we have this. And so what we see is, what this tells us is that that inner piece that we have, that whole thing that we're looking at the limit for, is greater than or equal to this negative square root x cubed plus x squared, and it's also less than or equal to the positive version of that. But now we squeeze it. So we take the limit, notice we're talking about the limit as x approaches 0. We look at the limit as x approaches 0 of negative square root x cubed plus x squared. And hopefully what you notice is that you can plug in 0 and you get 0. And you can do that to the other side as well. The limit as x approaches 0 of this positive x cubed plus x squared. You can plug in 0, come out with a real number, it's 0. So now we have the limit on the left-hand side of this is 0, and the limit on the right-hand side is 0. And so what that tells us by the squeeze theorem, so by the squeeze theorem, there's nothing else that our limit can be, because we've now just squeezed it. So by the squeeze theorem, the limit as x goes to 0 of, last time I got to write this, sine of pi over x times the square root of x cubed plus x squared is going to be 0. And what I can show you is the line that is all squiggly, that is actually our sine of pi over x times the square root of x cubed plus x squared. The function that is doing this is actually the positive square root of x cubed plus x squared. And then this bottom piece here is that other side. So notice that we have truly squeezed that function that we have inside our limit with a top piece that's always y values are always greater. The other one, the y values are always less than. But yet we know the limit as x approaches 0 of those two functions. So it squeezes our function that we were finding the limit of to tell us that that limit must be 0. And that's the squeeze theorem, and that's section 1.6.